speaker. I'd like to speak about Dr. Andrew Harp. He was an undergraduate here, graduated in spring of 2012, and one of our sharpest students that I honestly say, one of our sharpest students that have come through this department. We're really excited to see Andrew go off into graduate school. He went away from here as a volcanologist and continued that passion, but we've seen he's kind of come back to reality, and now he's more of a structural geologist, I guess I would say. But
structural volcanologist.
Structural volcanologist. But along that tour that he took, can I get the lights? Andrew started out, this was him in his first field class, wondering, should I really be a geologist? And then I would say he got really excited, and he said, all right, I get to be outside, and but it's cold, but he liked it. And then from there, he went on to being a happy field geologist that you can see through there. So we've enjoyed the journey that Andrew's had. He went on to SUNY, State University of New York, Buffalo, to get his master's in 2014, and now his PhD. And he's obviously teaching structural geology for a lot of the students who are here. So we're very excited to have Andrew here to talk about his PhD research. And with that, I'll hand it over to Dr. Andrew Harp. Thank you.
All right. Thank you, Todd, for that introduction and throwing me for a loop for the beginning. So let me try to get back on track with where my thought process was going to be. I left Chico. This was a great place, and for those of you who are planning on to go to graduate school, I just want to say a few words. First of all, you guys are extremely lucky to have your undergrad or to do your graduate degree here. Doing my master's and PhD on the East Coast and teaching structural geology and field courses to students from over there, you guys have it made compared to living in Western New York and seeing the same 4 units day in and day out. Flatline. We were excited to know that one of the units in the area were dipping at 2 degrees, and it's all just carbonates. And so when we take the students out to do field camp, they're completely blown away, completely overwhelmed with the complexities of the geology out here in the West. And so consider yourself very lucky. And if you really want a leg up, go to an East Coast scroll for graduate, and they will think you are the smartest person because you've seen faults and you've seen what outcrops look like. So like Todd said, I went to the University of Buffalo, and it was a huge change for me in lots of different ways. It snows there, and it didn't snow that much here, and this was one of our first years, or one of our first winters here. With 6 feet of snow in like 3 days, and it was awesome and terrible all in the same sense. But I do want to tell you that my graduate career, my funding was completely unorthodox, and it seemed like for all the RAs that I did, I never got paid to actually do my research. I always got paid to do something that was completely irrelevant to my research. So one of the projects I worked on was building this system here, and this is me. We worked on magma water interaction experiment, so we would pour melt from a furnace into a container, and then we would mix it with water and try to get it to explode. That's nowhere near the structural volcanology stuff that I talk about or that I do my research on.
But very cool.
But it was very cool, and it paid the bills, and so I did whatever I needed to do. Another project that I worked on was using explosives to create craters to study Mars diatremes, and then to also investigate eruption column collapses in volcanology. Again, something that's completely different from my research background. But if you make yourself available to people, if you never say no, if you're always shaking hands and meeting people and showing them that you're a hard worker, that sort of thing goes so far that they will just offer you money, because they would much rather take somebody who doesn't have any background in those types of research over somebody who maybe has a lot of background but is not a hard worker. And so I originally went to Buffalo completely unfunded, and by the time I left, I was on TAs and RAs, just because of doing the hard work, putting in the time, shaking the hands. And so I just wanted to kind of say that before I started into the rest of the stuff, that it doesn't all have to be funding, TAs and RAs right when you go there. Okay, so like Todd said, I did my master's there at Buffalo, and it was first started off my kind of background in structural volcanology. That's what I'm going to call it, structural volcanology. And my master's research focused on an area in Nevada called the Lunar Crater Volcanic Field, where there are basically basaltic vents of various different exhumation, various different amounts of erosion. And there was this completely uninvestigated scoria cone that had been eroded down to the plumbing system. But there were also locations where the eruptive deposits were still preserved. So you have both the plumbing and the eruptive deposits right next to each other, which is kind of a special situation. And so my master's work was basically going through and doing detailed geologic mapping, like 1 to 1,000, even in some locations 1 to 500. Very detailed mapping, because the units were, it was a really tight system. The whole exposure is only about a mile wide, but you have dikes on top of dikes on top of dikes. And also mineral fabric analysis of plagioclase crystals within the intrusions in order to try and determine propagation direction of those intrusions. And so what ended up happening was I went through, spent some time reconstructing the edifice, reconstructing the eruptive episodes of that particular volcano. But kind of a side note that came out of that was that there was a significant lateral transport component of the magma within the scoria cone. In other words, a lot of the magma that was erupted out of the scoria cone did not come out of the summit, but instead came out on the flanks of the volcano. And that was actually what contributed a large part of that 26-kilometer lava field there. And so that was kind of a side note. It wasn't the main purpose of the project, but it led to, it had this existing questions that it left in my brain. Why did that happen? Does that happen in bigger systems? And why does it happen in bigger systems? And so when I decided to do a PhD, this is the questions that I wanted to start tackling. And so I wanted to focus on bigger volcanic edifices, like stratovolcanoes. And stratovolcanoes would be like Mount Shasta. Mount Shasta is a typical stratovolcano. I wanted to investigate the transport of magma within those systems, because they also have flank eruptions, which come out the side, as well as summit eruptions. So why does the magma decide to go out the top rather than out the side, or vice versa? And so the main questions that I have were, what influences do the stress fields and the magma overpressure have on the propagation direction, geometry, and the spatial distribution of radial dikes and other intrusions within the stratovolcano? Another question I had was, what are the host rock conditions that exist within the central portions of the volcano, here, that can promote magma transport either to the summit or out towards the flanks? Now, to kind of sum it all up and put it in perspective, what I was really interested in was, how does magma first propagate into the volcano? Okay, how does it get into the volcano? Then, how does it propagate through the volcano itself and ultimately feed eruptions either at the flanks or at the summit? So to kind of step back and give a little bit of an introduction, So my project was looking at stratovolcano plumbing. And this is the system that transports magma from whatever crustal reservoir it's been stored in or was generated in up to the surface or up through to the volcano. And I focused on the shallow portions of this plumbing system, which would be the upper several kilometers of the crust and within the edifice itself. Now, the shallow plumbing system is mostly going to be transporting magma through tabular features called dikes. So these are sheeted intrusions that are oriented high angles to bedding. So they're not sills, they're dikes. And this is an example of what a dike looks like, an exhumed dike in Spanish Peaks, Colorado. So I wanted to investigate these dikes and how they transport magma through volcanoes. Now, there's a couple different types of eruptions that you can have at a volcano. First off, you can have a typical summit eruption. That's what we think of, in most cases, the conceptual model for a stratovolcano is that there is molten material coming out the summit, right? Just like that. But there's also flank eruptions. And this is where magma intersects the surface not at the summit of the volcano, but lower down on the flanks, okay? And you can get instances where the intersection of the dike happens lower down. That's where the eruption happens. That's where the material comes out. Now, for summit eruptions, the magma has to pass through the central portions of the volcano in something that's called the central intrusive complex. Okay, so in order for it to get to this summit, it has to pass through the central intrusive complex. And what we know about the central intrusive complex mostly comes from eroded volcanoes and from operations like this where they drilled, actually physically drilled, down through a recently active central intrusive complex, in Japan. And what has been found is that basically this area at the center of the volcano is made mostly of multiple different types of intrusions, stocks, dikes, sills, within a host rock of breccia. Okay, and that breccia can either be eruptive breccia, so it's breccia that has filled the vent after large eruptions, or it can be breccia that's formed by the actual physical breaking up of intrusions by later intrusions. Now at eroded volcanoes, these are the best places in order to investigate the central intrusive complex because these drilling operations are basically a one-dimension analysis of the system. You basically drill a pinhole through the whole complex, and you really don't get any idea for the distribution or the orientations of intrusions within that complex, as well as any variations in the vertical direction. And so we do have some information about central intrusive complexes at eroded volcanoes, but often any studies that mention these are part of these larger mapping projects or where the detailed mapping of the central intrusive complex is not the main goal. So maybe they're looking at hydrothermal alteration or something along those lines. And so there really is a gap in the literature regarding what exactly the host rock conditions are, what exactly the orientation and distribution of any of the intrusions are, and how that results in affecting any later intrusions that may want to come up through the center of the volcano. Now, flank eruptions, like I said, occur below the summit of the volcano, and these are often going to be fed by what's known as radial dikes. And radial dikes are oriented around the volcano, so we're looking kind of a 3D cross-section here. Radial dikes are oriented around the volcano like spokes on a wheel. And the orientations for them are going to be controlled by the principal stress directions. And they're going to be responding to whatever the local and regional stress field is oriented like. So local stress field perturbations can occur from things like the gravitational loading of the edifice. Okay, that can result in radial dikes. Or pressurization of a subsurface reservoir can change the stress field in the area and result in radial dikes. Regional stress fields can also affect the orientation of dikes, and that would be something like whatever the tectonic regime is. Now, the current conceptual model that we have for dike propagation is going to be based mostly on historical and geophysical observations. So there are two main types of emplacements that are known in the conceptual model. Basically, there's lateral propagation of dike. So the dikes propagate from the center of the volcano outwards towards the flanks, and when they intersect the surface, they feed an eruption. The other type are just vertical dikes. So these dikes come up from a subsurface source, okay, somewhere below the volcano, and just vertically come up and intersect the flank of the volcano itself. However, these historical and geophysical observations are really coarse in any type of detail that can lead you to any continuum between these two. Basically, they're only left with the possibilities of it had to propagate laterally or it had to propagate vertically. That's basically the resolution that we can get from geophysical data like surface deformation or seismic or magnetic or gravity data. Any type of those geophysical techniques can really only resolve simple end members to these types of dike propagation. And there exists a whole host of questions, but they can be kind of focused down to what governs the dike propagation. What governs lateral versus vertical? Why would one dike want to propagate one direction rather than the other? And also, like I said before, is there a continuum between these two? Is it really that there's just lateral and vertical dike propagation, or is there going to be something in between? Also, what is more common? Are most of the flank eruptions that we have in volcanoes fed by lateral dikes, or most of them fed by vertical dikes? Cool. Now, this is important because those dike propagation directions, those variabilities in the different directions that they can propagate leads to significant uncertainties regarding the vent location. Where the dike intersects the surface, that's where the vent's going to open. So therefore, the location of the vent is dependent on the propagation direction of the dike. And as you can see, there's a lot of different options that we can have for dike propagation just based off of the vertical and lateral propagation model. Now this leads to really significant problems when you're trying to do things like eruption forecasting or hazard assessment on stratovolcanoes. Because there's a possibility that you can get vent openings or intersecting of these dikes really low on the flanks of the stratovolcano. And of course, that's where everybody lives, right? So you can get conditions where a vent basically opens up in the middle of a subdivision, like in the case here. This is a shield volcano, but the process is similar. This was fed by a laterally propagating dike with a source somewhere up near the summit. And it eventually intersected the surface in the middle of the subdivision. No kidding. And this has happened several times in many different volcanoes. It happened in Etna, it's happened in the Democratic Republic of Congo, on volcanoes where people have built up or live up on the side, and most of the eruptions have been happening at the summit, but then all of a sudden you have a flank eruption that opens up in your backyard. Also, lower down on the volcanoes, you can have interaction with the aquifer. So as the dike is propagating towards the lower portions of the flanks, it may interact with the shallow aquifer. In that case, you can get conditions like this eruption in Japan, where you had a phreatic eruption, or you could even get phreatomagmatic eruption, so a mixture of the water. And that can lead to what would normally be an effusive eruption to turn to an explosive eruption such as this. And again, look at the infrastructure that exists. This basically opened up in a town. That sort of thing can be devastating. Another problem is that the conceptual models that I talked about, that lateral and vertical dike propagation, that was basically built upon a handful of Italian volcanoes. And that's because those volcanoes are highly active, they're easy to get to, people have been living on them for thousands of years, so there's been lots of observations. And so there may be this bias towards the propagation direction of dikes at those specific volcanoes when the conceptual model for radial dike propagation was built. And then finally, flank eruptions don't have to be mafic in composition. They don't have to be effusive in their eruption nature. This is an eruption of a volcano in Japan, Sakurajima. This is a flank eruption. And this is a Plinian column, okay, which is, in the volcanology community, a really large eruption. Also note that there was a similar column on the other side of the volcano. In this eruption, you had two flank eruptions open up on either side of the volcano. And this was an intermediate composition, highly energetic, lots of dissolved volatiles that drove a significant eruption. If this sort of thing were to open up in a community, it would have probably happened relatively quickly, and there would be massive impacts on loss of life and infrastructure. Now, in order to investigate these intrusions and try to determine these propagation directions and their influence by the stress fields, I went to a few different field sites. First site I went to was in France. So this is Puy-de-Sancy. It's up there in like the ski region, the Auvergne region of France, but it was an eroded stratovolcano. And it had lots of exposed dikes that looked like kind of stegosaurus backs and things. That was really interesting. I also traveled to Mount Vesuvius in Italy, where there are dikes that are exposed in the walls of the crater of actual Vesuvio, as well as in the Soma from the older Edifice. Okay, those are dikes that propagated through a stratovolcano. And then finally I went to Mount Etna, where at the time that I was there was an eruption that was going on. It was a small flank eruption, and so we were able to go up to the vent and look at the lava flows and that sort of thing. But there were also locations where erosion has exhumed dikes at that volcano as well. And so we were able to make observations and detailed descriptions of those dikes to try and figure out the stress field. Now, the biggest field area and the most important one for my project was this volcano called Summer Coon in Colorado. And so this is located in, if you guys can see it, it's located in south central Colorado, it'd be in the San Luis Valley, west of Pueblo, up there in one of those big valleys. And this was a mainly basaltic andesite stratovolcano. It was very typical of what we would imagine like a medium-sized stratovolcano would be, approximately 14 kilometers in diameter with a maximum height of approximately 2 kilometers. And what has happened is that erosion has removed the upper portion of the edifice. And so the current exposure is a roughly horizontal exposure through the base of the edifice, approximately 300 meters above the basement. Now, what this gave me was the opportunity to study the horizontal distribution of intrusions within the volcano, whereas the other field sites were only vertical. Okay, so we were only able to look at like vertical walls. This was the opportunity to look at the horizontal distribution. Now, this is what the geologic map, a basic geologic map of the area looks like. And what we can see is these thicker lines, okay, these are evolved radial dikes, whereas the thinner black lines, those are mafic radial dikes. There's approximately 30 andesitic, rhyolitic, rhyodacite evolved dikes, and approximately 700 of the mafic dikes. So a lot of those mafic dikes were available in almost 100% exposure. A few sagebrushes and junipers and rattlesnakes, but besides that, you were almost looking at 100% exposure, which is awesome for these types of big scale investigations. Also, at the center of the exposure was the central intrusive complex. So we had a slice through the central intrusive complex. And within there, it's been mapped at kind of a basic scale, part of a couple exploration type investigations. But they're located in the central intrusive complex as a set of stalks and other smaller dikes. Now, I first started off by working on the mafic dikes, the more numerous of the mafic dikes. They're really widespread, and so if I wanted to investigate the stress field, okay, the stress field dictates the orientation of the dikes, right? And I have exposure all around the volcano. If I want to investigate how the stress field affected the propagation of the dikes, then I want to gather as many samples as I can. And the mafic dikes offered that opportunity. They were also relatively simple and relatively short, okay, on the order of about 500 meters, which is nice and simple relative to the evolved dikes, which could be up to 6 kilometers long. And you can have all kinds of problems when you're trying to investigate those for propagation directions. So what I did was I collected samples from approximately 77 dikes. Okay, and those dikes were located at various azimuths around the volcano and at various different distances from what I inferred was the center of the volcano. And the sample collection involved cutting basically a 3 by 3 by 3 centimeter billet from the outer chilled margin of each sample dike. And the chilled margin is going to be basically the first part of the magma to solidify. Okay, so as the dike comes upwards, the first part of the magma that touches the wall rock, it's going to chill and it's going to record that magma flow at that certain position. And so what I did was I cut an oriented sample from that outer chilled margin. Okay? Had to be carefully oriented relative to all kinds of things, but what I would do is then make a thin section of each one of those oriented samples, all right? And then photograph, under cross-polarized light, I would photograph the plagioclase crystals that were preserved within that chilled margin. Now, plagioclase has the benefit of being a long aspect, which will typically orient at low angles to flow direction because of the shear forces that are generated near the wall of the dike. And so if you can get an idea of what the overall fabric is of the plagioclase crystals within the sample, and that sample is collected from the chilled margin of the dike, and that chilled margin is the first thing that's going to chill when the magma is intruding, then you can get an estimation for the propagation direction of the dike. Okay, so through some statistics, then I was able to calculate basically the mean fabric angle for each one of the sampled dikes. Now remember, when I'm talking propagation direction, a dike is a sheet. Okay, it's a tabular feature. And the orientation that I was interested in was the inclination angle between the propagation direction and the level of exposure, which is pretty much horizontal. Okay, I'm not talking about the dip of the dike, the strike and dip. Okay, the strike is radial, the dip is subvertical. All right, we're interested in how did that dike propagate subvertically, or did that propagate at a more inclined angle? That's the angle that I was measuring with the fabrics. Now, the results of this work indicated that the magma flow was dominantly inclined. All right, and it plunged both in and out away from the center, or in towards and away from the center of the volcano. So if we imagine a typical volcano, okay, with the center, something like that, I'm saying that the flow fabrics were plunging both in towards the volcano center and away from the volcano center. Okay, does that make sense? So in towards and away. These are the plunge angles of those flow fabrics. Another completely unexpected result was the fact that a lot of the dikes were concentrated in a zone approximately 2 to 3 kilometers away from the center of the volcano. It was a really, I mean, it had never been documented or measured before or mentioned in any previous studies, but we found that there at Summer Coon. Now remember, the flow fabrics that I'm measuring within the plagioclase, those are only lineations, okay? So they don't have a direction. They plunge in towards or away from the center of the volcano, but those don't immediately apply which direction the dike was actually propagating. In order to do that, we had to make some interpretations based on historical evidence, and then also comparing these to previous studies that had used things like anisotropy and magnetic susceptibility to determine the propagation direction of specific dikes. Now, when I'm talking about historical evidence, I mean that there's probably not a situation where a dike propagated from the outer flanks down into the center of the volcano, right? There's no geologic condition in which that exists. So in that sense, this meant that this dike probably went the other direction and out like that. This one, it's a little bit more complicated. We'll get to that. So for the dikes that had outward plunging fabric angles, we infer that most of those dikes propagated downwards along inclined paths. And that would mean that the source of the magma had to be higher up in the edifice. So this would likely be the result of an existing eruptive conduit, so you had magma stored within a conduit, or this could be a condition like at Kilauea, where you have a intra-edifice magma reservoir in that case. The other possibility is that dikes that plunge outward and away from the center of the volcano propagated upward and toward the center of the volcano. But that's probably less likely because that's propagation into an area that has a higher stress field. Okay, so there's a higher normal stress here because you have more stuff on top of you. So why would a dike want to propagate into an area with more stuff, more or higher normal stress? The opposite should be true. It should want to propagate towards the direction of least resistance. For dikes that had high fabric angles, or those that had inward plunging fabrics, we infer that most of those dikes propagated upwards and out toward the flanks of the volcano. Okay? These sources were probably down somewhere below the center of the volcano. But the major finding for this was that the dominant propagation direction was not subvertical, which was really interesting. That's how we think of, in most cases, dike propagation. It's either going to be lateral or it's going to be subvertical. Here, almost all of them were inclined in some way. So this led to that question, well, why did these ascending dikes propagate along inclined paths? Why didn't they just propagate subvertically? Some previous work that had been done at Summer Coon on one of the more evolved dikes indicated that there was probably a normal stress barrier that existed near the base of the volcano. So this normal stress barrier is an unfavorable location for the dikes to propagate through. So instead the dikes stalled and propagated instead sub-horizontally, basically trapped by that normal stress barrier. Now this has been kind of backed up by analog modeling, okay, that exists, but really there's very little analog modeling that exists, or numerical modeling for that sense, that exists investigating this type of propagation. Okay, lots of things on like the dips of dikes, but not on the along strike propagation direction. Now of the modeling that exists, they found that the magma propagation, or the propagation direction, was relative to the overpressure within the dike. Okay, whether it's high or low, the relative overpressure. And overpressure is just how much pressure is within the magma is available to drive that dike. All right. So the overpressure in the magma, when it's relatively high, you're going to get dominantly subvertical propagation. But when it's relatively low, you're going to get something like stalling, or even in some cases, sub-horizontal propagation. And so we infer that the dikes that propagated at relatively high angles, so subvertically through the level of exposure, probably had relatively high overpressures. But this was actually an uncommon condition at Summercoon. And instead, most of the dikes had relatively low overpressures. And instead of propagating up through the center of the volcano, which has the highest normal stress, they instead were deflected outwards towards the flanks, where the normal stress and the overburden is relatively low. So that would have been the prevailing condition. And then this is consistent with the observations that dikes probably generally have low overpressures, because most of them never make it to the surface. Most of them are going to be trapped within the subsurface. So the other portion of the project that I worked on was looking at magma propagation through the central intrusive complex. And what we found was that of the many different types of options for magma propagation, we found that the dikes within the central intrusive complex can be broken into three main groups. Okay, so these are the dikes shown here in the black lines. The first group, group one, these dikes are relatively short, okay, and they don't include andesite. These dikes here, group two, are basically the medium length dikes, and they cut all the way through any of the central stalks. Group three, which is the longest of the evolved dikes, none of the group three dikes penetrate all the way through to the center of the central intrusive complex where the stalks are. So there are no group three dikes that cut through the stalks. And the interpretation for that is that basically group one and group three are the two end members for the possible propagation directions. Group one dikes propagated subvertically, and they were able to propagate through the relatively competent, the stiff stalks, okay, because they had likely higher overpressures. Dikes that propagate vertically, subvertically, if you think about the geometry of a dike, those dikes are going to be relatively short and outcrop-like, and they should be located the closest to the center of the volcano if they propagated along subvertical paths. And then the opposite is true for dikes, for group three dikes. These dikes likely propagated along inclined paths in the most proximal relative to the center of the volcano. Okay, this inclined path drove them out and away basically from the center of the edifice. And basically what they were doing was that they were unable to penetrate through the relatively competent stalks. The stalks were too stiff in order for them to propagate through. So instead, they kind of rode the edge all the way up to the level of exposure. That's what drove them outwards. And it's once they intersected the level of exposure where that inferred normal stress barrier existed, they then transferred into pure subhorizontal propagation, propagating outwards and away from the center of the volcano. And that's why they have such long outcrop lengths. So to sum up, basically the dikes within the central intrusive complex, the shorter ones, okay, the group 1 dikes, these propagated subvertically, driven by relatively high overpressures. Now those are the important dikes because they have the potential to feed summit eruptions. But we're talking dikes that were only 500 meters long. Okay, and a 500 meter long dike within an edifice that has a diameter of maybe 16 kilometers, 20 kilometers, that is really difficult to try and image using geophysical techniques. You would see that there are earthquakes there, but you would have no idea that a 500 meter long dike is propagating up through the central intrusive complex. Yet, those were probably the dominant dike lengths that fed summit eruptions at Samarkand. And then group 3 dikes were important because these dikes did not ever make it to the summit. Instead, they were able to propagate way out onto the flanks of the volcano. And there are certain locations where they fed eruptions 7 or even 10 kilometers away from the center of the volcano. So in which case, you may see that there are seismic signals that are indicating magma migration near the center of the volcano, but you end up with an eruption 10 kilometers from that location and way down inside your town or wherever it's located. The other thing was that these dikes probably were driven by low overpressure, which makes sense because they were dominantly andesitic in composition. An andesite would have been the more mafic of the evolved dikes, which in general sense should result in a higher density. The higher density, less buoyancy, less overpressure. Okay. And that sums up the talk.
You had a quick question.
Yeah.
You said at the end. So early on you said you mapped the 2 different types of dikes. So are the mafic the younger ones then?
The mafic are actually the older dikes of the evolution of the volcano. So it actually follows kind of a reverse differentiation. So it started off mafic, then it went to rhyolitic, and then it went to intermediate. That's what the stratigraphy says.
But the diorite would have been, the stock in the center would have been older than the mafic intrusions?
It would have been part of the same eruptive condition, so the same port timeline of the volcano. So the volcano is dominantly basaltic andesite. So it was pretty much built up to its largest height early in the composition evolution. So mafic dikes, mafic basaltic andesite, breccia, and then the diorite and the stocks, the mafic stocks were in place. Then it switched to a different composition and had a few dikes and a few eruptions of more evolved compositions.
Do you see any fabric associated with the paleomagnetics?
With the paleomagnetics, so I didn't do any paleomagnetic work out here. There has been some anisotropy of magnetic susceptibility work, but there has not been any paleomagnetism that's been done on the basaltic andesite dikes. Oh, sorry.
No.
I was wondering if there was, if you found a trend within like the angle of the incline dikes. Is it a continuum of like subhorizontal all the way to subearth, or did they fall into a small?
So they were concentrated around about 45 degrees. So there were a few high angle dikes and there were a few low angle dikes. So they were kind of right around the middle. So, and that, you know, that we have some theories as to why that is, but it may be reflecting of like whatever the angle of the slope of the edifice was. And stratovolcanoes tend to have kind of the similar slopes, just based off the material they're made of.
You decide.
Oh, I get to decide now?
Yeah.
Oh. Yes, sir, you in the front.
So you're equating this overpressuring with composition. Well, you're not equating, but you're trying to get degrees of overpressure from the composition, whether it's andesitic or not. And I'm wondering, and I understand that, but are there other ways you can overpressure an injection besides just with the mechanism that you're thinking about?
Right, yeah, you definitely can. So when I was, so I'm not necessarily saying that, I'm just saying that the group 3 dikes, those are the only dikes that were andesite.
Yeah.
And so those dikes maybe had the lower overpressure. I think that all the group 3 dikes had low overpressure.
Are there other
but
ways?
it just makes sense that the andesite ones were in that group. The other ones did not include any andesite. Andesite was not able to erupt through the center of the volcano.
Are there other ways you can indicate the pressures that the magma was undergoing or feeling?
Yeah, the easiest way to do it is to use the length and the width of the dike.
Mhm.
So dikes that are short and fat, those have the highest amounts of overpressure.
Okay.
But you have to make a few assumptions about the host rock and the depth of emplacement. And that may be possible with the more evolved dikes, but you can't do that with the basaltic andesite dikes because you don't really know how big the edifice was at any given time. And for these, you know, there's a lot of assumptions you would have to make as to what its depth was at any particular point.
Right.
Because here, you have the normal stress is decreasing along the same dike. So these dikes, and it has been shown, these dikes do increase thickness, which means that there was a lower normal overpressure. Yeah. Yes?
I have a question, maybe a little bit strange, but you were showing in the beginning the flanks, and then you had mentioned about groundwater, and they were really explosive. And I'm wondering if you have found any differences in the dike formations in environments where the where there was a higher groundwater saturation as opposed to that which was more arid.
I haven't personally. I know people that work on that sort of thing that are really interested in the interaction, especially for the Mar diatreme. Because I mean, those are volcanoes that are driven exclusively by the interaction between magma and water. And so I know they have done more work on it. I didn't look at that specifically here. I mean, most of the dikes, the basaltic andesite dikes were mostly unaltered, whereas a majority of the evolved dikes were altered. Now, whether that says something about the hydrothermal conditions that exist, maybe, but that was beyond the scope of what I was really looking at. Yes?
Can you explain again why you get that change from subvertical to subhorizontal at essentially the basement edifice interface?
Yeah, so.
And then
Okay.
And then why is it, or was it just happenstance that Summer Coon happens to be eroded down to within 300 meters of that? And did you see similar types of dikes on other stratovolcanoes that weren't erupted down that far?
Okay, so your first question deals with this basically this elbow here, right?
Yeah.
So the interpretation for dikes 3 was, or group 3, was that proximal to the center of the volcano, this inclined angle was due to the stalks.
Okay.
However, the stalks cannot explain this elbow here. And the dikes had to come up from somewhere. So the dikes had to have come up from the subsurface. They did not propagate from the center of the volcano outwards, okay, because they don't extend into the central portions of the volcano. So they had to propagate from inclined to subhorizontal propagation at about the level of exposure, which is pretty much, I mean, it's only 300 meters above the basement, so it's at the basement.
Right.
in the scale of things. And there are lots of different explanations for why that happens. So the biggest one, the current buzz, is the level of neutral buoyancy. So you have such buoyancy in your dike, and once it reaches a host rock of equal density, then it basically can't propagate upwards anymore. You go to zero buoyancy. But if you're still injecting material, it's got to go somewhere, so it goes subhorizontally. That doesn't work with this model because the edifice is made out of the same stuff as the basement is. So you can't explain that in that sense. So you have to deal with something else. And the most logical explanation is that the normal stresses that are generated by edifice rotate the direction of the principal stresses at the base of the edifice. So you get to a point where sigma 3 is roughly horizontal. They want to expand, they want to propagate perpendicular to sigma 3. But if you all of a sudden then make sigma 3 vertical, then the dike is going to want to go horizontally. It's going to want to propagate as a sill. And dikes don't like to transition that way. So you're basically trapping it at a certain depth. Just because you're changing the conditions above it, it doesn't want to propagate upwards. But just like the level of neutral buoyancy, if you still are injecting material into it, it's got to go somewhere. It's not going to form a balloon. That doesn't make sense with the stress. So instead it will choose to propagate outwards towards the area of lower normal stress. Now when you get to like the dike level, like the conditions at different locations on the dike, we can talk about that later because that's an area of future work that I want to work on. But it probably has something to do with, at one point of the dike, you have a lower or a higher relative overpressure because the normal stresses are less. So you're going to propagate faster in that direction and slower in the areas that have higher normal stress. And the overall sense is that it propagates outwards.
And you just happen to get lucky with your
So
was
right,
eroded
so going back to
down.
that situation,
Yeah.
some raccoon is just lucky, but I've been to many edifices where you're not in that condition. You're down here, where you have mostly vertical dikes. You have short dikes, which probably didn't propagate subhorizontally. Or you're up here, where you still have a mixture of everything. But it just happens that at that level of exposure, things wanted to propagate subhorizontally. But it's basically at the basement edifice transition. So it would make sense that there's going to be something happening there.
All right, well, let's thank Dr. Harp for a great talk.